In this video, we are going to explore the second major aspect defined in the IEC 61131-3 standard, the data model and variable declaration. If you missed the previous videos in which the standard basics and software model are described, check out the links in the description. A PLC program is fundamentally the manipulation of memory. To do this reliably, we must understand the technical specifications of the data types defined in the standard. A variable is a symbolic name associated with a specific memory location. When we declare a variable, we are providing the compiler with two critical pieces of information. Number one is the data type, how many bits of memory to allocate and how to interpret them. And second, the scope, which parts of the program are permitted to read or write to this memory. In this video, we are going to explore the elementary data types supported and defined by the standard. Choosing the correct one is critical to prevent overflow errors and to optimize the memory usage in your application. So let's start from the classic, most fundamental variable, the Boolean. This represents a single binary logical state. It can only have two values, 0 or 1, also called false and true. While logically it occupies a single bit of memory, most systems allocate a full byte or 8 bits for addressing efficiency. Then we have bit string types. These values are the concatenation of multiple bits. We have the byte, that is made of 8 bits, the word, that is made of 16 bits or 2 bytes, the D word or double word, made of 32 bits or 4 bytes, and the L word or long word, made of 64 bits or 8 bytes. Although they occupy the same memory space as integers, they are not interpreted as numerical values. Instead, they are treated as raw bit patterns. These types are essential when you need to pack multiple Boolean flags into a single variable, or perform bitwise logical operations using masks. Then we have integer types, used to represent whole numbers. The key distinction among different types are the memory size and whether or not the type is signed. Signed integers can represent positive, negative, or zero numbers, while unsigned can only represent zero and positive numbers. All unsigned types in the IEC 61131-3 standard start with the letter U. So, starting from the smaller sizes, we have the short integer that occupies 1 byte, SINT for the signed version that can range from -128 to 127, and the UINT for the unsigned version that can range from 0 to 255. Then we have the 2 bytes integer, int for the signed version and UINT for the unsigned one. The 4 bytes double integer, dint for the signed version, udint for the unsigned one, and the 8 bytes long integer, lint for the signed version, ulint for the unsigned one. The choice of the correct integer requires caution. You should use a type that is large enough to avoid the overflow during calculation or representation of the maximum value that you require, while considering also memory efficiency. Also, mixing signed and unsigned integer in calculation requires caution, as implicit conversion may lead you to unexpected results. Dint and udint are very common for general purpose use and provide a good enough range for most applications. Then we have the real types, that are used to represent numbers that may have a fractional part, using a floating point format, for which there are two versions. The real variable, a 32-bit floating point single precision variable, with approximately 7 decimal digits of precision, and the long real variable, 64-bit floating point double precision variable with approximately 15-16 decimal digits of precision. A crucial data type in automation is the time variable. Since many temporized actions or sequences may occur in a PLC program, using times to set up timers and delays is crucial for a PLC programmer. The time variable represents a time interval or duration. It is declared using the literal syntax t hashtag followed by a value and a unit of time. D for days, H for hours, M for minutes, S for seconds, and MS for milliseconds. For example, t hashtag 2s indicates 2 seconds, t hashtag 500ms indicates 500 milliseconds. Internally, most PLC systems implement the time variable as an unsigned double integer that stores the duration in milliseconds. You should know that whenever you need to carry out some calculation using time variables, you can add them, you can subtract them, but under the hood you should know that they are unsigned double integer most of the time. Other less used types of variables are used to represent a time of day, a date, or a combination of both. You may find that manufacturers implement their own version of this rather than following what the standard provides as a guideline. So you should not, in my opinion, waste too much time learning how the specific time of day or date and time is implemented in the standard. Since most of the time, if you're working with a specific manufacturer PLC, you may find a different implementation. Then there are the string variables that are used to represent sequences of textual characters, useful for setting some text to be displayed or to carry out some encoding for communication protocols. The most commonly used is the string type, that is a variable length variable in which each character is encoded inside a single byte. Beyond these standard data types, the IEC 61131-3 standard supports derived data types, allowing programmers to create arrays that are indexed collections of variables of the same type, or structures, collections of potentially different data types grouped under one single name. Choosing the right data type ensures your machine can calculate values correctly, but knowing what data to store is only half the battle. You also need to control who can see and interact with that data. If you want a comprehensive list of the variable types supported by the standard, among other informations, check out my book, PLC Programming for Beginners, on Amazon. A link is in the description. So in the next video, we will cover the variable scope, local, global, input-output variables, and we will see how the visibility is important when interacting with variables using program organization units.